Okay, so far in review, I'm looking to get my pen right here. In review, we looked at statistics from the sample, and we calculated descriptive statistics. I don't know what just happened. We calculated them, and we graphed data. And we made histograms. Everything we've done in the past has come from the sample, and the samples are they're always representing a population. And we like the samples to be randomly generated. So when they're randomly generated, they represent a random variable. And I usually call those RV capitalized. And so those random variables, are how we talk about the population. And using those random variables, we can get parameters. And I talked about this earlier on in the beginning of the class. Whoa, I don't know what I'm doing there on spelling that. Let me erase that. That does not say parameters. That says paradigmers. How about this? There we go. We get the parameters. And some parameters are from, let's not write from, let's say describe the population. So P and P, right? Parameter for population, just like sample and statistic went together. And the parameters that we can talk about are mu, which is the mean, sigma squared, which is the variance. We can also talk about sigma, which is the standard deviation. So it's really no different from the sample. It's just that now within the population they have kind of Greek symbols to represent that you're inside the population instead of Arabic symbols to represent that you're in the sample. We are going to talk about the mean, the variance, and the standard deviation of a population of a random variable kind of in the next section of our book, because we're moving into the inferential side. and the inferential stats have us use the stats to make conclusions about parameters. And we have not done that yet. All we have done is found descriptions of the stats and not really used them to do anything. But from the beginning of the semester, I talked about that we want to use those statistics to talk about the population, and this is how we get used to doing that. We first introduce the parameters of the population that we'll be interested in, and then we'll move into how do we get the descriptives to talk about those parameters in the population. So one thing we need to do to talk about is that random variables, they can be discrete or continuous. And your book has talked about it a little bit up until now. I have not, but I want to clarify that now. So discrete means that let me erase that, write it better. A random variable takes on unique values. For example, a discrete random variable may be oh, sorry, I thought I hit eraser. Days of snow. And the values of the random variable can be no days of snow, 1 day of snow, 2 days of snow, 3 days of snow, up until you get maybe a full 365 days of snow. But each one of these are unique, the 0, the 1, the 2. What I really mean is we can't have uh, 1.999 or 24.5. No in-between values there. So that if you're looking at the random variable x, it's just 1 or 0 or 2 or 3 or 4, just up until you get to the 365. And there's no kind of in-between. So we can't have a smooth curve. So no smooth curve fits x. Versus a continuous random variable is where you can get its values form an interval, which is more how we think about things. And as an example, a continuous random variable may be the height of men in US. And that height of men in US, you could have, right, that they're 6 foot tall, or that they're 6 foot 1 inch, or 6 foot 1.2 inches, 6 foot, 1.5 inches, etc. So we have not unique things, but all the height of men in the U.S. follow a smooth curve. For instance, something that maybe looks like if this is 0 and this goes all the way to, I don't know, maybe 96 inches. Well, not very many men are 0, right? Then all of a sudden they start to come up and then they go down like this, right? So we have a smooth curve. Representing x, the random variable of the height of men. And this matters because the way we deal with the parameters, discrete and continuous random variables, are dealt with differently. So that's what we're going to talk about really in chapter 6 of the Agresti textbook. So what I want to do is talk about discrete random variables have what's called a probability density function. And this is how we represent the values of x. Okay, so as an example, we may have x and then p of x, which is the probability of the outcome equal to x. And we build an xy chart where maybe x is 2 and x is 5 and maybe x is 8 and x is 10. And the probability of being 2 is 0.10. The probability of being 5 is 0.50. The probability of being 8 is 3.30, and the probability of being 10 is 0.10. What's key to notice is that the sum of p of x always equals 1 or 100%. And you can see here that it definitely, if we sum all those up, we get 10%, 50%, 30%, and 10% definitely makes 100%. Or 1. So that's something that is a quality of a probability density function that's very different from any other kind of function that you may have encountered in previous math classes. So that if we graph this probability density function, where this axis is p of x, just like f of x when it was a non-density function, but just a typical function, then and this is our random variable x, and the values it can take on is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That at 2, and this is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and so on. At 2, we have a 0.1. At 5, we have a 0.5. At 8, we have a 0.3. And at 10, we have a 0.1. And this is a probability density function. As you can see, it's very discrete. because it just is these little bars. What you should note is this graph that I just did is not a histogram. Histograms come from the sample, probability density functions come from the population. So it kind of looks like a histogram, but it is not a histogram. It is a discrete probability density function. And from here, we can go on and kind of work within the, a discrete random variable. So if we want to find mu of a discrete random variable, it is found to be the sum of x times p of x. And what that means in our example is that you take the value of the random variable and multiply it by its height. So if you go back to the table that we just dealt with, we have the first one is 2 times 0.1 plus, right, the next one was 5 times 0.5, and then we had 8 times 0.3, and then we had 10, I think it was 10, let's look back, yep, 10 times 0.10. So you can go ahead and make that calculation. Sorry, that was my calculation machine not working so well. I dropped it. You can go back and just perform that calculation of, 0.2 plus 2.5, sorry, I got a little sidetracked, plus 2.4 plus 1. And then if you add all those up, you get 6.1 is the mean. And if you go back to the previous graph, you can see that the mean that we just calculated was 6.1. And that means that it's kind of falling right in here. And the mean is not one of the variables inside the probability distribution function, and you can see it's weighted over there closest to the 5 because the biggest density is here at 5, right? The tallest line is here at 5, so the mean is getting kind of sucked into that. And if we go into the variance and the standard deviation, the variance is found to be, I wanted to make sure I could find the formula inside a textbook here. The formula is sigma squared equals, and again, it's very similar to the samples kind of variance, where you take the sum, and in this case you have the data point, but you multiply it times p of x minus mu, and you square that for each one. So it's very similar to the variance of a sample. So in this situation, you would go through and you do 2, and then you would take the density function 0.1, and you would subtract off 6.1 and square it, and then you would add to that the value of 5. You would take the density at 5, which is 0.5, you would subtract off 6.1, and then you'd square it, and then you'd add to it 8 times its density minus the population mean and square it, and then do the last one, which is 10 times its density minus 6.1 squared. And then I'm going to do that real quick and kind of show I'm going to not show all the work, but some of the work here. So I have 0.1 minus 6.1, and then I'm going to square that, which is 2 times 36, and then I'm going to add to it 0.5 minus 6.1, and I'm going to square that, equals 5 times 31.36 plus, I'm going to do 0.3 minus 6.1, and I'm going to square that, which is, there's an 8 here, 8 times 33.64, and then I have the 10 times the last one, 0.1 minus 6.1. So I just wrote that formula wrong, which is why I'm sort of pausing. Let me just back up. Just back up. I don't want to start the lecture all over. I apologize for that. Sometimes I catch myself in the middle of doing something funky chicken, and I don't want to start a whole new lecture over here, even though it's an online class, so I'm just gonna, I had a moment there. Okay. The formula for the variance is the sum of x minus mu squared times p of x, which is very much like the sample standard deviation. It's just the probability in the sample is that it's always 1, so you didn't see it there, but it was always x minus x bar squared. So this is the same thing, and again, I apologize for that previous sort of funky chickenness that I was doing. This is going to make the numbers make a lot more sense. So I have 2 minus 6.1 squared times the density of 0.10 plus the next one, which is 5 minus 6.1 squared times its density. This is making much more sense in my brain as I work forward now. And this is 8 minus 6.1 squared times its density, and then we'll add to it the last point, which is 10 minus 6.1 squared times its density. And we end up getting, I'm going to do that work, I get 2 minus 6.1 equals 64, so I get 64 times 0.10 plus, now I'm going to do 5 minus 6.1 and square that, is 1.21 times its density. And you can see that that 5 in the graph was really close to the 6. That's why that number's really close, that 1.21. And then the third one is 8 minus 6.1. And I'm going to square that. And I get 3.61. And I'm going to multiply that by its density of 0.3. And then I'm going to add to it the last one, which is 10 minus 6.1. And that's 15.21 times its density. So then when I calculate all those densities, I get 64 times 0.1, which we know is 6.4. The next one is 1.21 times 0.5, and we get 0.605. And then we get the next one, which is 3.61 times 0.3. which is 1.083, and then the last one is 15.21 times 0.3, which is 4.563. We then add all those up, and we get 12.651, which is the same thing as the sample. It has no units. So then we find sigma, the standard deviation, where we square root that 12.651. And once we take the square root of that number, it's 3.5568. And that makes a lot of sense. And what that means is, if you go back to the graph, the standard deviation is not that far off, because if you go like sigma is about 3.6, right? Kind of rounded there. And so if you go 3.6, you're sort of here on one standard deviation. The other way you get all the rest. Here, if you go 3 away from the mean, you're here and here. So we'll talk about those green dots and how I'm counting away from the middle of the mean. But these two numbers are pretty important parameters for this density function. And that's how we deal with a discrete random variable. The next lecture will deal with the continuous random variables, and only one in particular. Okay, I gotta figure out how to stop this from recording. F10.